Okay, so let's give you a quick review for previous class. In previous class, we focus on the interstitial mechanism and also the interstitial C mechanism in crystal structures and how to formulate the diffusivity of these diffusing atoms. So for the interstitial mechanism, the diffusing atom is the smaller solute atom, which you dope inside these materials. So this solute atom moves through interstitial side. So the energy barrier will be related to the lattice distortion. So the only energy we have here is a migration energy of these solute atoms, smaller solute atoms. So we can get the diffusivity of this solute atom expressed equals to diffusivity, which is a temperature independent term times the temperature dependent term. And inside this exponential energy enthalpy part or activation energy part is only regarding to the migration energy of this solute atom. But this is interstitial mechanism, right? But what's the interstitial C mechanism? Which means the diffusing atom jump through interstitial side and substitutional side. So always jump between substitutional side and interstitial side. This will drive the diffusing atom diffuse through these materials. So the difference between this one and previous interstitial mechanism would be the atom located at interstitial side actually is the same type of atom, is the host atom, totally the same type of atom with the host atom. So you can observe all the atoms are the same, but some atoms locate at interstitial side and some atoms locate at substitutional side. So there's a very important characteristic here. The diffusing list must have a self-interstitial defect nearby the diffusion atom. So this defect can drive the diffusing atom diffuse through your materials. So this kind of diffusion we call it is an interstitial C mechanism. So it turns out the presence of self-interstitial defects is quite important. So which means if you have more this self-interstitial defect, then the diffusivity will increase in the meantime, right? So the concentration of this self-interstitial defect play a very important role in diffusivity. So next, I'm going to show you what's the self-interstitial defect. How many different types of self-interstitial defect we have in our crystal structure. So let's take an FCC as an example. There are at least 6 types of interstitial defect in FCC, and A to C actually just you just directly insert the host atom in into the octahedral interstitial side, tetrahedral interstitial side, or in between these two phase center. And the DEF actually is we find that it was a lattice point, but we inserted 2 host atoms to share this one lattice point. So that will cause the DEF. Also have and based on the directions between these 2 host atoms, the direction of a linkers link these 2 atoms, so that will result different name or different kinds of self-interstitial defect. And the reason the textbooks introduce more and focus on the split dumbbell is due to they say that the reason is due to the lowest formation energy for this split dumbbell. And as you know, interstitial C mechanism is through the first criteria is all the atoms are the same, and let's have a self-interstitial defect. And here, the self-interstitial defect we talk about is a split dumbbell, which means the 2 atoms share one lattice point, and due to there's a higher formation energy compared to other other diffusion mechanism for like the vacancy formation energy. So this only happens, you can observe this phenomena or diffusion patterns in the high temperature. Okay, so and how to get the self-diffusivity through this interstitial mechanism? So first of all, it's highly related to the fraction of this interstitial defect and diffusivity of this interstitial defect and times the correlation factor F. So this is something, it's related, as you know, if you have more this interstitial defect, the diffusivity will increase, right? Or if the DI increase, then you can get the D star will be higher. So based on this, you also know that the self-diffusivity of the host atom is much smaller than diffusivity of this defect, right? Okay, so based on this, I'm going to give an example because we already explained more about, tell you how to get the self-diffusivity of the host atom through interstitial mechanism. So I'm going to give you an example here. The example here, we also, the question will be, we have 3 split dumbbell self-interstitials with 100 configurations in FCC crystal. So it tells you we have a split dumbbell self-interstitials. So you know, and the direction we have 3, right? And direction is 100, and use this symbol to label these configurations. So this implying that we have 3 different directions of split dumbbell self-interstitials, included 100, 010, and 001 direction, and also with the same concentration of the SD interstitials. They have the same concentration of SD defect. We use the 1 divided by 3 for each configurations. And we draw 2 FCC unit cell together and highlight the split dumbbell at the center of this phase. So the question here is, can you formulate the flux alpha to beta, beta to alpha, and the net flux in terms of total concentration of interstitials per univalent, and also the total jump frequency gamma? And also, can you formulate the diffusivity of the split dumbbell interstitials in terms of C gamma, and this is constant? So based on this, you know, the questions want you to get the diffusivity of this split dumbbell by using the fixed first law. So we already told you, is if you want to get the diffusivity by using the fixed first law, you need to get the net flux, right? In order to get the net flux, you need to identify 2 plane, alpha plane and beta plane, and write down the corresponding flux. From alpha to beta, flux from alpha to beta minus flux from beta to alpha, then you got a net flux. So as long as you draw this one, so we need to identify the plane, alpha plane and beta plane. To me, I will identify the alpha plane at the plane we put the split dumbbell. So we put the split dumbbell at this plane, right? So this we call it is alpha plane. And the beta plane here I choose is the middle or the center of this FCC, unit cell of FCC. Because what? Because this is to this split dumbbell, it can jump to the nearest substitutional site, right? For this is FCC, so we got 4 substitutional site on this beta plane. It's a phase center, and so also phase center, right? So I will consider this as a beta plane. Some people probably were curious about, why, Professor, why don't you use this plane as a beta plane? If the split dumbbell want to jump here, you need to make a 1 jump, 2 jump is not suitable to use this as a beta plane. As we mentioned, the atom always jump the nearest substitutional site, right, to make a successful jump. Okay, so based on this, And in order to formulate a flux, though, just a quick review, the flux equals to possible jumping directions times jump frequency or jump rate in one direction, and times the area concentration. And don't forget, you need to convert the area concentration into the volume concentration to compare with the fixed first law to get the diffusivity. So as long as you already identified alpha plane and beta plane, so let's try to formulate the flux from alpha to beta. Don't forget we can have 3 different directions of split dumbbell, so we need to consider them one by one. So let's focus on the split dumbbell along 1, 0, 0. So it's 1, 0, 0. We show it in red. The possible jump directions. So what's the possible jump directions to jump to beta plane? Don't forget lattice point is here. So we have a atom slightly in front of this lattice point and slightly back from this lattice point. So in order to jump to the beta plane, so it probably will jump to here. This one will jump to here, or this atom will jump to here. So there are 2 possible jump directions. So we got the 2 gamma prime. And the concentration here is C prime divided by 3. And if we take a look on the 0, 1, 0 split dumbbell is shown in blue, then this for sure the atom can jump, the atom on the alpha plane can jump to beta plane for sure is this one, right? Because this one is far away from, far away from beta plane. So this one has the nearest jump distance, so can jump either this for substitutional sign. So we got the 4 gamma prime, and the concentration also C prime divided by 3. And regarding to the split dumbbell along 0, 0, 1, how many possible jump directions allow this split dumbbell to move to or jump to beta plane? The upper portion, the upper atom can jump to this side, right? And the bottom one can jump to this side, because actually this is higher and lower away from the lattice point. So to the upper atoms is showing us a distance to jump to this location, substitutional side, and this one can jump to here. So we got the 2 gamma prime, concentration C prime divided by 3. So we sum this up, we got the 8 C prime gamma prime divided by 3. But as I mentioned before, C prime is the area density. So in order to compare with the volume density, we need to divide it. We need to convert this C prime in terms of C by times the A divided by 2. Let's consider this balance. Okay, and next, you can convert it, because in the question they want you to express in terms of gamma. So gamma prime need to convert it to gamma. So you need to back to the coordination number for this split dumbbell. In previous this one, we know Z equals to A, 4 plus 4, right? So we substitute with this. You express this in terms of gamma, C, and A. So now you know the flux from alpha to beta. So now what's the beta to alpha? As I mentioned, in order to maintain or remain the concentration gradient along y-axis to compare with fixed first law, so we need to modify the concentration. We need to show the concentration on the beta plane by C plus the distance A divided by 2 plus the concentration gradient. So use this minus this one, then you got this one, and compare with the fixed first law, then you got the diffusivity in terms of lattice constant and jump frequency, total jump frequency. Okay? So this is we successful to answer question 1, question A regarding to the flux and net flux, and the diffusivity is question B. So regarding to the question C would be the people is going to apply a stress along x-axis on these materials. So apply a tension stress. And when the stress is released, the concentration of 3 self-interstitial will repopulated and reach the state with a uniform or even concentration of interstitial defect. And please show the relaxation time for this repopulation is expressed like this. So the first thing is, do you have any idea if you apply a tension stress along x-axis, what's the concentration change for these 3 different directions of SD defect? Do you have any idea about this one? As you learned before, I believe that will be the last part in chapter 2, right? When you apply, if it is an interstitial atoms inside the compressive region, then this interstitial will be pushed toward to tensile region. So if I apply a tensile stress on these materials, then the interstitial atoms will move along this x-axis from 2 other directions. So you can expect the concentration of 100 SD defect will be larger than the other directions. So the concentration of 100 for sure will larger than C total divided by 3. Then, as long as I release this stress, then the concentration of 100 split dumbbell will decrease and back to C total divided by 3, right? So I asked you about the relaxation time. So let me draw something. So if this is 3 and C total, so when I apply a stress, the 100 S split dumbbell concentration will be higher than C total over 3. How high will depending on the how much stress I apply on this materials. But when I release the stress, I use different color, then I can expect the concentration will decrease, right? And back to reach a steady state means the concentration, C concentration divided by 3. So relaxation time is this concentration minus C divided by 3 and the E1 over E. The relaxation time. So if I assume the concentration is A, so it will be A minus 3 C total and times E reciprocal of E, or E2 minus 1. This concentration, when the concentration reach this concentration, so the time tau we call it the relaxation time. Okay? So this is the idea. So what's the relaxation time? When the concentration back to the E2 minus 1 of original concentration. What's the time? This time we call it a relaxation time. So based on this, you know, as long as I release the stress, then the split dumbbell will jump back to other directions, including the 010 or 001, right? Because the concentration along 100 is higher than the other directions. So I can formulate these reactions. The 100 probably will jump to 010 or jump to 001. Or, for sure, in these complicated systems, 010 also have chance to jump to 100, and 001 also can jump back to 100, right? So, in order to know the concentration of 100 split dumbbell as a function of time, so I need to formulate these two reactions and get the concentration, how the concentration change with time. The equation related to how the concentration 100 change with time. But here I want to explain more. Some people probably will ask, Professor, why you will think about, you come up with this idea to formulate this relationship instead of starting from fixed first law or diffusion equation. Because the question here asks you about the relaxation time and also the concentration of 100 split dumbbell, right? So first thing come up from your mind will be you need to get what? You need to get the concentration profile as a function of time. But if you're starting from fixed first law, what you will get? You will get the concentration as a function of location, right? But this one the question is not asking you to answer the distance, the locations, how the concentration change with location, right? But the other idea probably was, Professor, how about use the diffusion equation? But don't forget the diffusion equation happen in non-steady state will involve what the concentration will change with time and location. It's nothing, and we don't have the location part, right? So you cannot use both those approaches to answer these questions. So based on that, I will suggest you to use this one because let's follow this reactions we just show you. The concentration change as a function of time can be expressed like the rate constant. The rate constant K1 is a SD change from 100 to 010, and the backward or reverse reaction is K3. And also 100 probably will change to 001, so the rate constant we call is a K2, and reverse one we call is a K4. So based on this, both these reactions, we can formulate the concentration change with time can express like a K1 from here, right, times this concentration plus K2 times this concentration. And the backward will increase the concentration of 100, so it will be minus K3 times this concentration and minus K4 times this concentration. So if you check these equations, the one we show you here just related to the time dependency, right? So as long as I can solve this equation, I can get a C 100 as a function of time is what we are interested in, right? But now the question here would be, Professor, you have two unknown parameters, 010 and 001. If you want to get the concentration of 100, you need to put all the parameters, try to convert all list to 3 parameters to 1 parameter to 100, right? So that's I'm thinking about, is that possible to do something? But before that, some people are curious about rate constant here. Rate constant here, what's a rate constant? It's a possibility to tell you how many possible jump rate to allow this SD defect along 100 to jump to become 010, right? So the rate constant actually is proportional with jump rate. So you need to investigate how many possible jump directions to allow SD 100 to become 010 or to become 001. So in order to answer this one, so I will draw, let's take a look on the first one, 100. So I draw the 100 SD, and how this 100 to become the 010. 010 is along y-axis. So the possible way for this split dumbbell is the green one. Either jump to this one directions, will have 010, or jump to this directions, or the red one can jump to back face center or the other back face center. So for this split dumbbell 100 have 4 directions, possible directions. So we got 4 gamma prime. So the reverse one, if you try to draw it, also 4 gamma prime. Means the 010 jump, want to jump back to 100, also 4 gamma prime. And related to 100, jump to 001. So 01 is along z axis. So it for sure will be jump to upper. So this one, direction 1, 2, or the red one can jump to upper and jump down. So also 4 gamma prime. So the reverse one, also 4 gamma prime. So we got K1, K2, K3, K4 is 4 gamma prime. So if you try to reformulate this one, you got the 8 gamma prime, 4 gamma prime, 4 gamma prime. But here, yes, we already converted K1, K2, K3, K4 to the 4 gamma prime, right? So now the question will be the one I just mentioned. The parameter we still left 010, concentration of 0 along 010 and 001. In order to solve this equation, we need to convert these 2 parts into series along 100, right? So we play a trick here. We play a technique here. We put a technique here. What we do, because we know that the C total means the total concentration of split dumbbell remain constant, and also the sum of all 3 directions. So here, in order to get rid of this these 2 directions, so we minus 4 gamma prime C100 plus 4 gamma prime C100. We minus and plus. N will be 0, right? But we can put this together, so got the minus 12 gamma prime C100. And this 4 is quite important. We got the 4 gamma prime C total. So now C total is a constant, so we allow this equation to become 1 parameter in terms of C100. And next, I just want to solve these equations. So I check the mathematics books and find that the similar equations here. And the solution for these equations show like this. So here, the Y is a C100, the A is 12 gamma prime, and the B is C total is a parameter. So the solution for this one, so the only unknown parameter will be the K, right? So how to get the K? When T equals to 0, so you can get the K equals to the concentration of this ST defect along 100 minus the B actually is this constant, is C total divided by 3. So we rewrote the results here, and this is the K, right? So as I mentioned before, the question here is what's the relaxation time for this repopulation? So as I mentioned, the relaxation time is the T equals to 0 minus the C divided by 3 times the exponential. So based on this, we know the T should be 1 divided by 12 gamma prime. And gamma prime, we need to convert it back to gamma, so we got the results here, show it here. So this is the whole story. And in order to help you to practice this, so I'm going to give you an example here. The one we just focus on the deviation part, right? And this one would be give you some real data to hope you can really calculate something. So here what we have is we have a copper materials, and we know there's a SDD fat with alone 3 directions. And we assume the gamma prime is 10 to 8 per second, and that is constant. And also we already give you the concentration of split dumbbell and also the concentration of the copper. So the first question is asking you about the diffusivity of this SDD fat. And the question B will be calculate the self-diffusivity of copper through this interstitial C diffusion mechanism. So this is, you need to get the DI, and this D will be what? You need to consider the XI, DI, and F, right? So this data is for your reference. But the question C here will be a little bit different from previous example. A previous slide is instead of subjected to tensile stress, here we subjected to compressive stress along 100. Compressive stress tell you that the concentration of the SDD fat along 100 for sure will be smaller, less than 2 times 10 to 12. Yes, it is smaller or less than, right? Is 1 to 10 to 12. I already told you the value. And I asked you to calculate the concentration of SDD fat along 100 after when I releasing this compressive stress for 0.5 nanoseconds. So you need to formulate the concentration as a function of time, then put all the information inside, then you can get the concentration of this 100 SDD fat after releasing the compressive stress for 0.5 nanoseconds. Okay, so just for your reference. But I want to remind you, regarding to the relationship between the stress and the concentration part, you can check the last section in the lecture 2. In that part, we give you some example to how to estimate the concentration as a function of stress, right? Okay, so you can check that.